Good afternoon, everyone. I am Nikhil Raj Deep, a PhD student from University of Florida. So I'm going to talk about high resolution root zone soil moisture retrieval using UAV-based L-band radiometer. So in the morning session, we have already seen Dr. Ali have mentioned 4 satellites of comparison satellites, particularly SMAP, SMOS, SMRE. So these are all passive radiometers, and it has been proven that passive radiometers are very capable of capturing soil moisture. But these are at 0 to 5 centimeter depth. So the motivation for this research was to reach the root zone soil moisture. So the importance of root zone soil moisture is about identify the crop is under stress, irrigation efficiency, and the land atmosphere exchange. But the current limitation to measure root zone soil moisture is the in situ sensors, which lack spatial continuity. And the current satellite data which provides soil moisture is is like of coarse resolution and are shallow and have shallow sensing depth. Particularly SMAP, SMOS, they have 0 to 5 centimeter. And with this context, this becomes even more important coming to the Florida landscape, where the most of the landscape is sandy, which has low water holding capacity, rapid drainage. So in this scenario, root zone soil moisture is very critical. And this is the diagram which depicts what satellite sees and what actual root zone or the active root zone lies. The objective, so I have like 4 objectives. The first is to retrieve high resolution root zone soil moisture using L band frequency and convert this brightness temperature using tau omega radiated transfer model. The second is to identify the sensing or the effective sensing depth of L band radiometer over sandy agro ecosystems in Florida. And the third is to extend the near surface 0 to 10 centimeter to the root zone using equilibrium depth scaling function, and then validate these results. So this is the theory of passive radiometer concept, or the microwave emission theory. So here we are using HL6 drone. So we have mounted the L-band radiometer into it, and it is inclined at same SMAP angle. So it is inclined at 40-degree angle, and it captures natural emissions coming from the land in the form of brightness temperature. So we can clearly say, and to validate this, we have installed Acclima sensors at several depth, 10, 20, 30, 40 centimeters. Actually, I have installed at 5 centimeter, but in the schematic diagram, I haven't shown it. So this is the framework of tau omega, and it captures emissions from soil, emissions from vegetation, and it also captures attenuated emission from the vegetation, and it tries to minimize the vegetation attenuation so that it retrieves the soil emission. And this is the overall methodology. So for tau omega model, so from the sensor, we already have the brightness temperature value. So here it is denoted as TB. So for vegetation water content, so we have used NDVI. So we have used mica sense. In the same drone, we mounted mica sense and we captured NDVI over the potato field. And then we used soil temperature from the climate TDR. Then we did soil sampling, vegetation sampling. These are all the in situ and the field data collection. For the tau omega model, so it has some parameters. So we need to optimize certain parameters for to estimate soil moisture, particularly the surface roughness, because at each surface roughness changes, because potato is a furrow-based system. Surface roughness changes a lot in furrow-based system rather than a plain ground. And other parameters such as the vegetation optical depth, those are also been optimized in this forward tau omega model. And then once the parameter is optimized, we use the inversion approach, particularly using the single channel algorithm and converting the dielectric constant using the Mironov's equation dielectric mixing model to estimate soil moisture at 0 to 10, 0 to 20, 0 to 30, and 0 to 40 centimeter depth. And once we convert the soil moisture, we validate with the weighted average soil moisture which we install, which we get from the TDR measurements. And based on this, we identify the optical or the optimal sensing depth of the L band. And once we have the best depth, so we anchored that depth and we use that depth to further uh, extend it to the soil profile. And then we have the root zone soil moisture maps. So this is the method experimental design for the potato field. So we have used several sensors. So here we have installed PR2 access tubes across the field. So it is 45 PR2 access tubes. Other than that, we have additionally tested several other soil moisture sensors for like a comparative additional study. So we have used Teros 54 soil view TDR. And we Acclima TDR, so we have installed Acclima TDR at 5 depths, and all these are connected with the data logger. This data logger is simply like ZL6 Zintra, and we collected this data over potato growth period from Feb 20 to May 12, and each data were collected at 5-meter interval, but the flight have been conducted weekly. So these are the forward tau omega results. The simulated brightness temperature at 4 depth we can see at both polarization. SCA stands for single channel algorithm for V polarization and for H polarization. So we can see that 0 to 10 centimeter gives the better uh, uh, simulation for or the estimation for brightness temperature. And once we have that brightness temperature, we invert it to get the dielectric constant, and then using the Mironov's dielectric equation to convert soil moisture. So as we go below the depth, so the results is gradually decreasing, not substantially, or it's a gradual decrease. And clearly we can see that the V polarization gives produces the best TB and shows better estimation at 0 to 10 centimeter. Similarly, for the soil moisture also, the 0 to 10 centimeter provides the better accuracy. And with this quantitatively, we can say that, okay, at soil depth 0 to 10 centimeter, the effective sensing depth for this L band radiometer over sandy soil is 0 to 10 centimeter. So we have done another study. We have this is a qualitatively. So to quantitative analysis, we have done another study where we have mounted this L band radiometer over tower, and we have collected the data for the period of 3 months, and we identify the dynamic. So we identify few things. So SMAP assumes equilibrium time for 6 a.m., which is not similar for the field scale study. Another, we assume that SMAP assumes the emissions coming out from only top surface, which is 0 to 5 centimeter. But in our case, we found that from the tower experiment, the emissions were coming from 7 to it goes from 7 to 15 centimeter depth. So one thing was sure, that the emissions were dynamic, and it shows that it has deeper penetration in sandy soil, deeper emission sensing depth in the sandy soils. With these results, so this is the SCAV result for the 4th depth 0 to 10. So as it is a sandy soil, it is very clear that the top surface in the sandy soil is dry. So the values are, and then as we go deep into the depth, so we see that soil moisture increases. And this is a field scale tau omega inversion using radiometer, and this is at 1 pixel. So this is not at pixel level, this is a point scale data, but we have tried to change the flight planning so that we can have more dense lines and we can generate more finer soil moisture product. So each point gap is 1 meter here. And once we have that soil moisture, so from the accuracy metrics, we found that 0 to 10 centimeter shows the better result. So to say the effective soil moisture, so we say to have the estimated or the effective soil moisture, so we converted that L band retrieval to 5 centimeter here, so represented by the yellow dot in the line plot, soil profile plot. And then we use the equilibrium depth scaling approach. So here we are using a concept called hydrostatic equilibrium condition, and we used suction head at water table. So so with that condition, suction head at the water table is 0, and then in inverting or the optimizing the Van Gineken model, we identify soil depth at we converted this 5 centimeter to 10, 20, 30, 40 centimeter depth. So the uh, orange line, dotted line indicates the equilibrium depth scaling function which we developed. And since this is the original data, but with the site-specific calibration or the bias correction, we can improve this further. But our concern is that we don't want to use the site-specific calibration so that we can make it more generalized and it can be utilized in other study area also. So we are trying to develop something which we will be doing it in future. So we are trying to use hydrous. So basically we have collected each data weekly. So we want to estimate brightness temperature to fill. So let's say, for example, at 20 Feb, we have collected first data, and 27 Feb, we have collected the second data of L band. So we want to use hydrous to fill those days gap and try to find a new approach to avoid the site-specific calibration. So this is even in the site-specific calibration, we saw 10 centimeter, 20, 30 gives the reliable result, and 40 was not consistent. So the conclusion of this study is vertical polarization performs best for TB and soil moisture estimation. L-band radiometer over sandy cropping systems can sense deeper emissions. Equilibrium depth scaling function extends to the near surface retrieval into a continuous root zone profile, and the approach can be validated and reliable in sandy agroecosystems anywhere. And the future, yes, but what I mentioned earlier. So we want to couple this UAV-based brightness temperature measurements with soil water flow model simulations to improve the spatio-temporal resolution of UAV flights for root zone soil retrieval. Thank you. And so this research I conducted this year. We have also conducted research using UTV. So we mounted the L-band radiometer over UTV, and it was at 1 meter height. So we tested this over hemp experiment trial, and we got a better result here. So at each 10, 20, 30, 40 centimeter, we have a highly accurate result, and it's published. So we can, thank you. And one more thing to add. So I validated NISAR result for Florida, all the 3 products, and I found there was so the RMSE was 6%, and it was worse near the Everglade region, which has more clay texture soil. Yeah, thank you.
Right. Thank you, Nicole. Questions? Go ahead, John.
Yeah, thanks for the talk. Very interesting. So given that the B polarization outperformed H, as you wouldn't expect given the literature, can you comment on how you characterize surface roughness and the vegetation over the fields that you did your analysis over?
So you used
Um,
a tau omega model and you characterized vegetation with NDVI from a MicaSense.
Oh, yes,
So you're using NDVI, NDWI,
NDVI,
NDVI. And what was your, what was the crop again?
potato.
Like sorry, I did not know how big a potato
Okay.
is. I know it's mostly underground,
Yeah.
but the plant itself, like what's the magnitude of the vegetation?
Yes, so so we used SMAP equation for calculating vegetation water content, the polynomial equation, and the vegetation water content was the maximum was 2 kilogram per meter square.
All right. If there are no other questions, we can move on. Thank you, Nicole.
Yeah, thank you.